Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 continued, Structures of Covalent versus Ionic Compounds. So we're going to talk first about ionic compounds, and then we'll move over to covalent, otherwise known as molecular compounds. But ionic compounds, as the name suggests, are composed of ions. One part of the compound is positively charged and another part is negatively charged. The positive charged portion we call cations, the negative portion we call anions. And typically, if a metal is part of the compound, the metal is the portion that will become the cation. The metals are pretty stable when they lose electrons and become cations, whereas nonmetals tend to want to gain electrons in order to satisfy the octet rule. Remember, they're over on the right side of the periodic table, so they want to gain electrons to be like noble gases, whereas the metals are on the left side, they want to lose electrons to be like noble gases. So if we have two ions, a sodium ion on the left here, Na+, and you'll notice sodium ion has no electrons. It's already lost its one valence electron. Whereas chloride ion, and that's what we call it when we add the electrons to a non-metal, if we add enough electrons to make it like a noble gas configuration, in other words, full with its full octet, we end it with the letters IDE, and we call it this one chloride. Instead of the chlorine atom becomes chloride ion. So the chloride has its full set of 8. The sodium has 0, but it really has 8 from the previous row. So they both satisfy the octet rule, and now they're oppositely charged, and they attract one another. And that is the nature of any ionic compound. You'll have positive ions and negative ions attracting each other because of the electrostatic attraction where opposites attract. And this is not just between one sodium and one chloride ion. In fact, that sodium being positive attracts chlorides all around it, and the chloride being negative attracts positives all around it. And you end up making what we call a lattice structure. This structure where every ion is surrounded by ions of the opposite charge, making this large complex structure. And this would be the crystal, and this is why ionic compounds tend to form crystal solids, because they make these lattices whenever you have a collection of positive and negatively charged ions near each other. And so we don't really have a single molecule here. It's actually many positively charged ions in conjunction with many negatively charged ions. However, every different ionic compound has a very specific ratio between the number of positive charges and the number of negative charged particles. And because sodium is +1 and the chlorine being chloride is -1, they're in a 1-to-1 ratio. So if you look at this crystal, there are exactly the same number of chlorides, the green balls, as there are the sodium ions, the bluish purple balls. It's a 1-to-1 ratio. So instead of writing that you have this gigantic structure that has a bazillion sodiums and a bazillion chlorides, we just say 1 sodium, 1 chloride, and chemists, we don't like to write the number of 1 if we don't have to. So instead of saying Na1Cl1 to show there's 1 of each as a ratio, well, we would just remove the 1s and just say NaCl, and you've probably seen that formula for table salt before. So all ionic compounds are actually technically called salts to a chemist, but this particular one is what we know in everyday life as table salt. Now, there are other ionic compounds. There are literally hundreds, probably thousands and thousands of ionic compounds that are known. Here's one, magnesium iodide. It has 1 magnesium for every 2 iodides. So each magnesium is an Mg+2, and we'll get into that later. And each iodide is an I-1. So we have a 2-to-1 ratio. So the iodides are represented by the purple balls, the magnesiums are represented by the yellow-green balls, and if you actually started counting these, you'd see that there were twice as many purple balls as there are little green balls in this crystal because there are twice as many iodides per magnesium, and therefore we write the formula MgI2. So it's composed of one magnesium ion, which is the Mg plus 2, and two iodide ions, and there are many, many, many of these pieces, and we call these individual pieces formula units. The formula unit is the smallest ratio formula of that particular ionic compound. So in sodium chloride, NaCl is the formula unit. It's really many NAs and many Cls, but it's a 1-to-1 ratio. And it's really many magnesiums and twice as many iodides, but it's a 1-to-2 ratio. So the formula unit for magnesium iodide would be MgI2. But the reality is the structure has many, many more atoms than that. So in ionic bonding, sometimes you're going to have charges that don't match up. Calcium has 2 valence electrons. It wants to lose 2 and become a Ca plus 2 ion. Whereas nitrogen wants to gain 3 electrons. It has 3 spots left to fill that octet. So it wants to become nitrogen minus 3, what we call nitride. Remember, it ends in "ide" if we're adding enough electrons to make it satisfy the octet rule. So ides are only for anions that satisfy the octet rule for that atom. So nitrogen, which is shown here, nitrogen atom, wants to become nitride, gaining 3 electrons. Well, if the one on the left wants to lose 2 and the one on the right wants to gain 3, how do we balance that? Well, we balance that by having 3 calciums that each want to lose 2. That means they want to lose a total of 6 electrons. And we have 2 nitrogens on the right that each want to gain 3 for a total of wanting to gain 6 electrons. So we're losing 6 from the left, we're gaining 6 on the right. Everybody's happy in the end because the calciums will satisfy their octet rule and the nitrogens will satisfy theirs, but it'll be in a 3 calcium to 2 nitride ratio, and you end up forming a formula unit of Ca3N2. In other words, you have this crystal with many, many calciums, many, many nitrogens, but they're in a ratio of 3 calciums for every 2 nitrogens, and that would be its formula unit. And so let's move to the structures of molecular compounds, also known as covalent compounds. These are not made of ions. Molecular compounds don't have ions in them. There are no formally charged atoms in here. They don't have a true positive charge or a true negative charge. And what they do is they have a different strategy for achieving the octet rule. And the reason why that's important is molecular compounds tend to be made with nonmetals only. Remember, nonmetals are over on the right side of the periodic table. They all want to gain electrons. Well, if we have 2 chlorines shown here, these are 2 chlorine atoms, they each want to gain 1 electron. Well, they can't both gain 1 electron. If the one on the left gains 1 from the one on the right, well, then the one on the right will be missing not just 1, but it will be missing 2 electrons. Well, that doesn't make that chlorine happy, but it makes the chlorine on the left happy. So the solution here is that instead of stealing an electron or giving up an electron, they share electron. So if they have 1 space each that needs to be filled, well, they share 1 with their partner, and now you have a pair of electrons that are shared between the 2 atoms, and this, in fact, is what constitutes a covalent bond. So because we are sharing valence electrons, they are covalence electrons, we call these covalent bonds, and therefore this would create a covalent molecule, otherwise known as a molecular compound. So covalent compounds and molecular compounds mean the same thing as molecules technically. We don't usually use the word molecule when we're talking about ionic compounds. You might hear me or other chemists say molecules all the time. We do that in everyday speech, but technically ionic compounds are made of formula units and molecular compounds are made of covalent compounds or covalent bonds. So here's chlorine molecule, and now the 2 are sharing a pair of electrons. A pair of electrons is a single covalent bond. And what happens is the chlorine on the left thinks, and I'm going to use thinks again in an anthropomorphic way, thinks it has 8 electrons, because if you look at all the electrons around the chlorine on the left, it's a total of 8. But if you look at the chlorine on the right, it's also a total of 8. Yes, there are not 16 total, there are only 14 total electrons, but they each feel as if 8 are around themselves, and therefore each satisfies its octet rule, and the molecule is fairly stable as a result. So this would be the Cl2 molecule, or what we call chlorine gas, or chlorine. If I just said chlorine and didn't say chlorine atom, you would assume somebody says chlorine if they mean the chlorine molecule, Cl2. And I'll just tell you, this molecule, while fairly easy to acquire, this is actually a very dangerous molecule. If you breathe chlorine gas, it will do severe damage to your lungs and will frequently result in death within 24 hours. And this has happened to a few individuals who were sadly contaminated with this and breathed it in, and it formed hydrochloric acid in their lungs. So molecules, remember, molecules are composed of atoms that are bound together by covalent bonds. Molecules, just like atoms, are defined as being neutral, no charge. If we put a charge on an atom or we put a charge on a molecule, we call those ions by definition. So a molecule, you assume it has no charge unless somebody tells you there's a charge. As this contrasts ionic compounds, which the formula units have no charge, but the individual pieces do have charges. So each of the atoms in a ionic compound can have actual charges, but there aren't true charges in atoms that are in molecular compounds or covalent compounds. Here's another example of putting together a covalent compound. We have oxygen, which has 6 valence electrons, so it needs 2. And we have hydrogen, which has 1 valence electron, but it needs 1. Remember, hydrogen's on the top row. You only need 2 electrons because of the quote-unquote jokingly called duet rule, not octet rule for the first row. So oxygen just needs to get 1 in a share. And I'm sorry, hydrogen needs to just get 1 in a share, but oxygen needs to get 2. So how does oxygen get 2? Well, we use 2 hydrogens. They each want to share 1 electron and get an electron that's in exchange. And by doing that, now the oxygen will form 2 different bonds with 2 different atoms of hydrogen. So you have oxygen in the middle that is in a single bond with the hydrogen on the left, and the oxygen in the middle is with a single bond with the hydrogen on the right. Remember, a single bond is composed of exactly 2 electrons. You'll notice this oxygen also has other pairs of electrons that are not bonded. We call them non-bonded pairs, but more often we call them lone pairs or lone pair electrons. You'll hear that term a lot. So this oxygen has 2 lone pairs and 2 bonded pairs for a total of 2 bonds, whereas the hydrogens have no lone pairs and 1 pair that's shared, or 1 bond. Hydrogens typically form 1 bond, oxygens typically form 2. Chlorines and all the other halogens frequently form 1, but there are many exceptions for the halogens, especially if they're in the center of a molecule. So double bonds, which would be twice as many electrons as a single bond, would be 2 pairs of shared electrons. So a single bond is 2 electrons, 1 pair. A double bond would be 2 pairs of electrons, or 4 electrons. A triple bond would be 3, and we'll get to that in a second, but let's talk first about the double bond. Here's carbon in the center. It has 4 valence electrons. It needs 4 more electrons. Well, where is it going to get it? Well, if it interacts with 2 oxygens, they each need 2 electrons. The carbon needs 4 electrons, and you can imagine that they can come together and initially share a pair on either side of the carbon, but still, the oxygen on the left still needs another electron. The oxygen on the right still needs another electron, and the carbon in the middle still needs 2 more electrons. So the way around this is to share more electrons. So by moving those electrons in the center between the atoms, you now have a double bond between each oxygen and the carbon. That is, you are sharing 4 electrons between the oxygen and the carbon on either side of the carbon. You'll notice that in the end, the carbon has no lone pairs, no pairs that are not involved in a bond. All of its pairs are involved in bonds, whereas the oxygen still has 2 pairs of electrons, 2 lone pairs left over. Each oxygen does. Now, if you do the count, the oxygen on the left is surrounded by 8 electrons. You count all of the bonded electrons and all of its lone electrons. And the one on the right also has 8. You count all of its bonded electrons, the 4 bonded ones, and the 2 lone pairs for a total of 8. Whereas the carbon in the center has all of its electrons in bonds, a total of 8 electrons in bonds surrounding the carbon. So now each molecule has satisfied the octet rule, and you end up with this formula of oxygen double bonded to carbon, double bonded to oxygen, shown just above it. Now, triple bond, as I mentioned, is 6 electrons. It's 3 pairs of shared electrons. So we have nitrogens. They each need 3 electrons. Well, they can share 1 each, but now they both need 2. So they share another one, and now there's a double bond between them, but they still need to share 1 more pair of electrons. So they end up sharing a total of 3 pairs of electrons, forming a triple bond between the nitrogen. Remember, a single bond is 2 electrons, double bond is 4 electrons, triple bond is 6 electrons. And you'll notice each nitrogen has its own lone pair left over outside of the bonded pairs. So if we count them, the nitrogen on the left has a total of 8 around it. The nitrogen on the right has a total of 8 around it. They both satisfy the octet rule, so you end up with a stable molecule. In fact, nitrogen, or N2, or nitrogen gas, is an extremely stable molecule. It's very difficult to break this triple bond. It requires some really specialized chemistry to rupture that triple bond holding 2 nitrogens together. So nitrogen in the air, remember, nitrogen represents 78% of our air. It's pretty inert molecule. It's not completely inert. It does react a little bit with some things, most notably with microorganisms that live in the roots of plants can take this nitrogen and turn it into useful compounds that the plant can use for food. But humans can't do that. Mammals can't break apart nitrogen gas. It's incredibly stable. So let's talk about the 8 elements that are always found in pairs in their natural, what we call elemental form. In other words, the form that they're found when they're pure elements. And there are 8 of these in the periodic table. And what's interesting is if you find them on the periodic table, they form this pattern that we call the 1+7 pattern. The 1 on the left is hydrogen, and the other 7 atoms that form diatomic molecules, in other words, they group together in pairs, form a 7. The 7 form a 7. And it's easy to remember which 7 these are because they either end in the letters GEN, hydrogen, nitrogen, oxygen, or they're halogens, shown in the bright yellow on the right. And halogens, oddly enough, I know the word halogen ends in gen, but none of the halogens end in gen. They all end in the letters I-N-E, pronounced ein or een. So they would be fluorine, chlorine, bromine, iodine, and astatine. And those are the 5 halogens, and every one of these 8 molecules, when they're naturally found, appear as diatomic molecules, molecules with 2 atoms of these, in this case, of the same atom, 2 molecules of the same atom. Not all of them are gases. All of the gens are gases: hydrogen gas, nitrogen gas, oxygen gas, fluorine gas, and chlorine gas. So the first 2 halogens are gases. Bromine is a liquid. It's the only liquid among the halogens. There are only 2 liquids on the periodic table. You can see the color coding. Liquids are labeled in blue letters. So bromine, Br, and mercury, which is a metal, it's not a halogen, mercury, Hg, those are the only 2 elements on the periodic table that are liquid at room temperature. So there's 1 metal that's a liquid and 1 non-metal that's a liquid, and everything else is a solid or a gas on the periodic table, at least at room temperature. So we have these 8 elements, the 1+7 pattern. It's easy to find. They're all found as diatomics. And so our next module will be talking about how to actually draw those structures. Those structures with all the dots of electrons are called Lewis structures, and we'll stop here.